Hello, my name is Jahanshahi. I'm going to present ScaleServe, a scalable multi-GPU machine learning inference system and benchmarking suite. ScaleServe is a work in progress from systems optimization and computer architecture lab at University of California, Riverside. So there are a lot of multi-GPU inference system and benchmarking suite solutions for deploying machine learning applications efficiently and with a higher performance on this multi-GPU systems. This figure shows how these inference servers and benchmarkings are stacked on top of the software stack and ML frameworks and runtimes to provide efficient inference systems. NVIDIA and AMD are NVIDIA and AMD GPUs are widely used as GPU accelerators for in the systems, and each of them, AMD and GPU, NVIDIA and AMD GPUs comes with their runtime drivers and GPU products. There are, but NVIDIA source code for runtimes and drivers are not open source. So there is restrictions for inference servers that, especially, for example, Triton inference server that only is based on NVIDIA GPUs. On the other hand, there are inference servers that are platform or GPU agnostic. TorchServe is one of them, which uses PyTorch ML framework, and on the bottom it supports NVIDIA and AMD GPUs. So it's GPU agnostic, but it doesn't support multi-GPU serving system. The other ones like RayServe or TensorFlow serving are also GPU agnostic or runtime agnostic, but they haven't released any stable version for their product for AMD GPUs. So for these inference servers to be efficient, we need to orchestrate the system components throughout this whole software stack. And the problem that we have with NVIDIA GPUs and runtimes is that they are not open source. So we decided to use AMD so that we can orchestrate different components of the server throughout the system and make them more efficient. And we also propose ScaleBench that goes on top of ScaleServe, uses PyTorch ML framework and ROCm stack to carefully benchmark and characterize the server on the target platform and fine-tune different configuration knobs based on the system resources. So ScaleServe consists of two parts: ScaleServe, which provides a multi-GPU inference server, and ScaleBench, which provides a benchmarking suite and scripts for benchmarking the system. I'm going through the different components of the ScaleServe to discuss their design purpose and what they provide. So inference front-end is the front end of the server, which provides a gRPC API for accepting a request to do inference on the server. So we chose a gRPC API because most of the state-of-the-art servers provide a gRPC API. This component is responsible for accepting the requests, allocating and responding with inference results. This is a multi-threaded process. We have a pool of threads that accepts the requests and waits for the results from backend to respond to clients. So these thread pool can be configurable, and we have one instance of this component per model in the server. The other component of the ScaleServe is a shared memory component that is responsible for storing request and response data as it flows throughout the pipeline. The configurable knob here is the queue size. We can adjust the queue size per model. Each of these components, request and response queues, are instantiated per model. In ScaleServe, we have two main controllers to basically enable enable concurrency. These components are batcher and queue manager that are designed to make the ScaleServe flexible and easily extendable. I'm going to talk about each of them later. So queue manager is a thread-safe interface that manages the allocation and deallocation of space from the request and response queue. And it also provides a notification policy for batcher. So each request that enters this system by inference front end, the batcher has to be notified somehow based on some policy that the request arrived the server. The batcher is responsible for batching the requests and passing them to the worker threads, the backend. The configurable knobs are here in this component are batching policy, which can be static or dynamic batching, batch size, or polling interval between for checking the queues. The backend is designed to basically provide a uniform API for different backends. For now, we are supporting PyTorch, but we are planning to extend the backends to support Onyx, TensorFlow, and MIGraphX. So this a component is a multi-threaded process, and this spawns worker threads that are performing inference throughout batchers. And we have one instance per model. And the number of threads, worker threads in this component can be configurable. So the scale bench part. So we add scale bench on top of the ScaleServe. The scale bench has a main component, which is a statistics front end. It also provides a gRPC API for requesting real-time server statistics. And this component collects the statistics from these shared memories that we have for each component, and calculates the metric based on the requested metric, that the requested metric type, and passes the results back to the client. So it is a process, and there is just one instance of this in the server. So in order to talk about the stats that we collect, this is the lifetime of the request that goes through the server. Worker, as they are spawned, they load the model in the requested GPU. They wait for batcher to receive a request and batch them. They they make the batch and pass it through the GPU. And at the end, they notify the front end to collect the results, which is a copy data here, and pass it to the client. So these figures show this figure shows the stats that ScaleServe and ScaleBench are providing. ScaleServe provides a real-time statistic, and this ScaleBench provides some benchmarking scripts to characterize the different components of the system. The stats that we provide are the symbol provided here on the right of the figure, and each component has their own statistics. So Q, for example, is the queue latency, which is from request arrival to response. We have the thread pool utilization in the front end, in inference front end. We have request response queue utilization stats, batch size stats, and CPU time, which is pre-processing data copy of the requests, and GPU time, which is the actual inference on GPU, which is shown by these arrows here. We provide mean, max, mean, average, and useful percentiles for benchmark for statistics for each of these statistics. But we noticed that adding the torch bands, scale bench to the server introduces overheads, and in order to remove them, we provided two development modes for ScaleServe, which is production and benchmarking. For benchmarking, we provide all the stats, which provides us detailed stats, but has more benchmarking overhead. But for production, we just have the queue time, CPU and GPU time, which provides higher level statistics, but lower benchmarking overhead. In order to evaluate our server, we ran an experiment for ResNet 152, which is used widely for backend of most of the computer vision tasks. Here is the spec of our server, and for ScaleServe, we fixed some configuration knobs to reduce the design space, our design exploration design space. So batching policy has been considered static. Pooling interval has been random per thread from 1 to 10 microseconds. Thread pool size has been 10, queue size 256. Batcher notification policy is per request. And we changed the worker threads from 1 to 8 for each GPU. Batch size has been changed from 1 to 128, and number of GPUs has been changed from 1 to 8. This chart shows there is the RPS that we obtained for ResNet 152. We changed the batch sizes. As you can see, the batch sizes are on y-axis, and this x-axis is, I guess, the number of workers. So the number of workers, we changed the number of workers, and we changed batch size and number of GPUs. As you can see, we have been able to scale. ScaleServe has been able to scale the RPS. Each number in these cells shows the achieved RPS, the max achieved RPS for that cell. So for future work, we are still planning to support more backends, TensorFlow, Onyx, AMD, MI graphics, and we are going to provide more detailed statistics from GPU driver and ROCm stacks. And thank you. If you have any questions?
Thank you so much, Ali. Any questions for Ali? So can you please explain how could you reduce the overhead in the production mode, deployment mode?
So in deployment mode, we basically disable all the threads that are in these components that collect the stats and store them in these stats shared memory instances. So in the production mode, we disable those threads.
Okay, I see. Thank you. Any question from audience? There is one question. Can this tool be used as a base model for DL scheduling?
Sorry, let me see. Can this tool be used as a base model? What is DL? What do you mean by DL? Dynamic load or?
Deep learning, I think.
Deep learning scheduling. Yes, so basically, queue manager and batcher, based on the policy that that set for them, they can they are basically performing a scheduler type of like task. Queue manager and batcher. So yes, we are doing scheduling here, but I'm not sure what you mean by DL scheduling.
Yeah. So I think I mean deep learning scheduling here, but I think my question should be asking this way. So say, for example, if I want to develop some new scheduling algorithm, can I just directly borrow your ScaleServe and replace some of the scheduling algorithms or batching algorithms that you use, and to say to test if the algorithm works on another platform, in other cases, or another scheduling algorithm?
Yes, yes. The components have been designed to be easily extendable, or you can modify them and plug your own scheduler into them.
Okay, thank you.
Any more questions?